Welcome to lecture 30. In this lecture, I will talk about gravitational redshift. Recall that in lecture 29, we found that photons get delayed when climbing out of a gravitational well. In this lecture, we focus on another curious property of photons that are climbing out of a gravitational well. The property we are focusing on is that photons get redshifted when they climb out of a gravitational well, which means that their color gets shifted to red as they sort of come out of the gravitational field of a central mass. The main effect here is very similar to the Doppler effect that you should be familiar with. If there's a car that's speeding along the road and it's honking its horn, it might sound like this. So you should notice that the pitch of the car is higher when the car is approaching and honking its horn, and it gets to be shifted to lower frequencies as the car is moving away. This is known as the Doppler effect, and it is a well-known phenomenon from everyday life. There is also a special relativistic version of the Doppler effect, which in particular applies to light. That is, if you see if you see an object that is emitting light, which is moving away from you, you will see its color to be redshifted. So, for instance, the color green might appear reddish as the object is moving away. By contrast, if the object is moving towards you, then the color that you see will be blue shifted. So, in particular, the energy of photons will be slightly higher than if the object was just at rest with respect to you. The Doppler effect in special relativity is an effect that applies to moving objects. Objects that move away from the observer appear redshifted, and the point that I want to bring to your attention in this lecture is that there's an additional, let's call it Doppler effect in gravitational theory, that is present also for non-moving objects. Note that this is similar to what we found in lecture 29 when we were talking about the time delay of objects in gravitational theory, which means that these are objects that are not moving, yet there is a time delay that is coming from the gravitational effect. To be concrete, let's now consider two observers which are located at the two values of the coordinates. Let's call them radius r is r1 and radius 2 r is r2 in a Schwarzschild spacetime. Let's assume that the observers themselves are not moving, so they are at rest with respect to the spacetime, and the velocity d vector x by dt is 0 for both observers. The observers have their own proper times, which are denoted by τ1 and τ2. And in particular, for observer 1, the proper time increment d τ1 squared is given by minus the line element, so minus g mu dx mu dx nu, evaluated at the location of the first observer, which is the radius r is equal to r1. Since the observer is not moving, dx is 0, so the proper time of observer 1 squared is equal to the Schwarzschild factor a of r1, because this is where the observer is located, times dt squared, where t is just the coordinate of the global time coordinate. Similarly, for observer 2, its proper time increment d τ2 squared is equal to minus the line element evaluated at r is r2. So that is, of course, equal to the Schwarzschild factor evaluated at r2 times the global coordinate dt. Since the global time coordinate dt is the same for both observers, we can solve for dt for observer 1 and for observer 2, and setting it equal gives us a relation between the proper time increment for observer 1 and observer 2. So in particular, from the first equation, we find dt squared is d τ1 squared over a of r1 for observer 1, and it's equal to d τ2 squared over the Schwarzschild vector evaluated at observer 2. So we find that there's a proper time interval for observer 1 and observer 2, which are different, and they are related by these ratio of the Schwarzschild vectors A, which I have now again written out in explicit form. So this relates the proper time increment for observer 1 and observer 2. Now, if there is an observer that is measuring some frequency, a frequency is nothing else but an inverse time interval. So this means that if the observer 1 is receiving or emitting a signal, which is then emitted or received from observer 2, the two frequencies that these two observers will measure are given by the relation, which is just the inverse of the relation for the proper time increments. So the frequency that observer 1 measures is given by the frequency that observer 2 has emitted times this square root of the Schwarzschild vectors. So the main point to consider is that here we find that the frequencies are different, even though the observers were assumed to be stationary, so not moving. So in this sense, it's different from the usual, in particular, special relativistic Doppler effect, because the special relativistic Doppler effect would not occur for observers or emitters that are stationary. If we want to consider a particular application of this formula, we can consider one observer to be very far away from the central mass. So let's take its radius R2, location R2 to be going to infinity. If we then do this and we denote its the frequency that observer 2 is measuring by omega infinity, we find that the frequency of observer of the distance observer is equal to the frequency that's emitted from the observer 1 at location R via this formula here, where R is the location of the observer and omega is the frequency with which the light source is emitted. So we find that there's this relation between the emitted frequency and the frequency that's received very far away from the central mass, and you can see that these two frequencies are not the same. In particular, since, assuming that the radius here is bigger than the Schwarzschild radius 2gm, this factor here will subtract something from 1. So then this factor is smaller than 1. And this means that if we multiply the original frequency omega by something that's smaller than 1, the frequency that's measured from the distance observer is smaller than the original frequency. Smaller frequency means less energetic photons. Less energetic photons means photons get redshifted. So we find that for the distant observer, the frequencies of the emitted photons appear redshifted. Just to reiterate, since both the emitter and the observer are addressed, the redshift is not the result of their respective movement. Instead, it's a gravitational effect. And we can come up with a fairly simple physical interpretation of why it is that this effect should be present. The simple physical interpretation is just energy conservation. So recall that a photon has a certain energy, and the energy of a photon is proportional to its frequency, omega, via this relation here. The energy of a photon is 2 pi times the frequency of the photon. However, if the photon is deep in the gravitational well, there's also potential energy that we have to add for the photon. In particular, if we want to sort of consider a photon that's climbing out of a gravitational well, there is a gravitational potential Gm over R that will lead to a potential energy for the photon that's negative. We can do a calculation that is easy to understand that just involves energy conservation in Newtonian theory of gravity. To this end, let's consider a photon with frequency omega at a position R in a gravitational well. Then the gravitational potential is Gm over R. So the potential energy of the photon in the gravitational well at a location R is given by the potential minus the potential energy minus the potential times the, well, if you want, so the mass of the photon, and the mass of the photon, of course, is related to its energy via 2 pi omega. So then the potential energy is this expression. The energy of the photon itself is 2 pi omega. So adding these two terms, we find that the total energy, meaning the energy of the photon plus its potential energy, is 2 pi omega times 1 minus gm over r. That's the total energy for a photon in Newtonian gravity. However, if the photon then is climbing out of the gravitational well, eventually it will reach infinity. And then if it is located at infinity, the total energy of the photon will just be the photon energy. So it will just be 2 pi omega infinity. And since there is no gravitational potential left at this far distance, however, since energy has to be conserved, the total energy after leaving the gravitational well has to be equal to the energy of the photon before leaving gravitational well. So that means that there's relation between the frequency at infinity and the frequency of the photon that was located at position R initially. So we find that in Newtonian gravity, we expect that the photons get redshifted via this factor 1 minus gm over r. Whereas in general relativity, we had a similar formula, except that there was a square root of 1 minus 2 gm over r. Now, if in general relativity, we expand this square root here in a Taylor series for small gm over r, we find that the first two terms, meaning 1 minus gm over r, precisely match the Newtonian expectation. But there are some additional terms that come from the infinite number of Taylor series coefficients of the square root. But the first two terms match, so we find that the calculation in general relativity indeed matches the calculation in Newtonian gravity for weak fields gm over r. And remember, the Newtonian calculation simply involved the conservation of energy. So that's why we expect a redshift of photons. The only difference is that we expect the gr result, the square root here, to be the exact result, whereas the Newtonian gravity calculation is an approximation. Okay, so we find that we have this redshift result, and if we now consider ordinary stars, so photon that's leaving, for instance, our sun from the surface of the sun, it will be emitted at the sun's surface or corona, so basically at a radius that typically is much, much bigger than 2 gm, which is the Schwarzschild radius of the sun. So then for ordinary stars, the redshift formula we find in GR is such that the ratio of the Schwarzschild radius and the radius is always very small. So the redshift factor is typically never extreme. However, we could sort of entertain the possibility that there are some strange bodies where a photon is trying to climb out of gravitational well very close from the corresponding Schwarzschild radius. So what if there's a photon that's climbing out of a gravitational well starting at radius r is equal to the Schwarzschild radius 2gm? Well, clearly, if we take the limit r goes to rs plus 0, then this ratio here becomes 1, 1 minus 1 becomes 0, and the redshift factor becomes extreme. So we find that for a photon that's climbing out of such a gravitational well, the frequency at infinity is going to 0. What does that mean? Well, if you have a frequency that's 0, that's an extreme redshift. It's shifting so far into the red that it's basically, basically first sort of go to infrared, then you go further down to radio, and eventually you find that for a photon that indeed is emitted from r is equal to the Schwarzschild radius, the frequency of or zero frequency photons are basically black. So we find that for this extreme scenario of a photon climbing out of such a gravitational well, the photon basically loses all its energy when climbing out of the gravitational well, and there's nothing left. The photon has 0 energy, it is completely black, and we will sort of basically not see this object even for any energy of the initial photon. So this can be a photon that has gamma ray energy. It will still come out as a black photon at the very end. Of course, this is an interesting sort of scenario, and it will actually turn out that there are real objects that have this property. These are called black holes, and those will be the property that we want to consider in the next lecture.